Hello class and welcome to today's video on using MATLAB's built-in genetic algorithm or GA function. So I'm going to walk you through this by using the same pendulum optimization problem we did in our first homework. So if we look over here on the editor screen, we can see the code that we used to run that pendulum assignment. So we have our quality constraints here, AEQ, BEQ, we set some options, we gave it an initial guess, we run the parameter, and we get our outputs. We can see that the syntax for the GA is very similar. Our output side looks the same. We now have GA here instead of fmin_con up here. We switch from the EOM in quotes to @EOM. The biggest change here is that whereas in fmin_con we have our initial guess x, this quantity here for GA is the number of variables. So there are 8 parameters that we were optimizing. Remember A1 through A4, B1 through B4. So we have an 8 here. This is basically the number of genes in our chromosome. We then have our same constraint options. So we see here if we hit run, it'll run through. And first, here's our solution that we all got using fmin_con. And the first thing we'll notice is that the GA is running. There is a fair amount of overhead on the GA. It seems to take roughly 30 seconds just to set up the GA and then a few more seconds to actually run through and allow it to complete. It does still say busy, and there we go. So that's one of the first things to point out, that fmin_con used 0.13 seconds, whereas our GA used 42 seconds. We see that our fitness value is actually a little smaller than the one found using fmin_con, but it is worth pointing out that, remember, one of the constraints is that this variable should have been 1, and this variable should have been pi/2, which is 1.5708. So the constraints are not held as tightly. So again, something we'll discuss in a little more detail. So some of the ways to fix these is by setting options. You see that we do not currently have any options set, and there are plenty of options that can be set using the GA. One of the best ways to discover these is if we type in help GA optim set. We see all the options that we can set for our GA with a description of what they do and then some information on accepted values and standard values. So we see, for example, the crossover fractions. This will be the P sub C we've been using. It will accept any positive scalar, and 0.8 is the default value. So to go discuss some that might be of interest to us, we can set our population size. So this was n from before, so we could set, maybe we want 50 organisms in our population. Generations, the maximum number of generations before termination. I usually like to leave this high if I set it at all, so say 1,000, to make sure that the other derived termination criteria are used. We can set the display to be on, so this would be, there are various display types. This just prints out some information after each generation. There are a plethora of plot functions we can use. This one shows the score for every individual at each generation, so we can track how that's progressing. We can set mutation, both in terms of how it handles mutation and the actual mutation rate. So say we could do uniform mutation, which is similar to what we use, and mutation rate is 0.01. Crossover fraction, as I said, is the P sub C, so if we wanted to keep that the same, we could change this value to 0.7. Use parallel allows us to use parallel processing. So if you have a machine that has more than one core, you can access those cores and allow the programs to run a little faster. So by saying use parallel to always, it'll take advantage of those multiple cores and run faster. Tolerance fun is the tolerance on the function, and this has to do with stopping criteria. Tol_con is a constraint tolerance. So we set this to a smaller number, the constraints will be more tightly met. So these are different parameters that we'll have an opportunity to investigate. For now, I'm going to comment this back out and I'll rerun it just using 1, showing that the tolerance has to be kept at 1 times 10 to the minus 10th, whereas the default, I believe, is 1 times 10 to the minus 6th. So now if I comment this code out and uncomment this, we have to add some extra empty brackets here, just as we did with fmin_con, and then we label the options. So now, if we run this again, we see once again we quickly obtain our solution from fmin_con, and once again it's going to take several seconds for the GA to run. So we can see our GA took almost 40 seconds to run. But we will notice now that our tolerances are more closely met. We can see we have 1 to at least 4 decimal places, and we have pi over 2 to at least 4 decimal places. And if we add these up, those constraints will be met as well. But in doing so, our fitness function has increased slightly. So this also helps to illustrate that when we have simpler problems like this, when gradient-based optimizations work well, GA isn't necessarily the best bet because it does take longer and we're not guaranteed to find the best solution. If we run this multiple times, we can find solutions that are closer to this 2.05 value, but again, there is no guarantee of that. We will see in a future assignment how more complex problems GA does outperform fmin_con. A final thing I would like to discuss, though, that is an advantage of GA is the full syntax of everything we can output and input to the GA. So our X value here, X is going to be the genes of our best chromosome. Fval is going to be the fitness value of that chromosome. Exit flag and output contain information regarding how the run went, how long it took, how many generations, why did it stop, what value did it stop at. We can also output population and scores. So population is the chromosomes from the entire final population. So say we had 50 organisms in our each generation, population would give you the genes for each of those 50 chromosomes in the final population. Likewise, scores will give you the fitness function for each of those chromosomes in the final population. So it is possible to get significantly more outputs, right? Because fmin_con only gives us a single solution. Whereas the GA, we can output the entire population, which means we would get 50 or 200 or however many organisms were in our population, we could get all of those scores. So we do get more answers at once, which is sometimes an advantage of GA. Over here on the input side, we can see we give it our fitness function, the number of variables, and number of genes that each chromosome has. AB sets up that A times X is less than or equal to B. AEQ, BEQ we've seen before, that AEQ times X is equal to BEQ. LB and UB stand for lower bounds and upper bounds. And we can set these that if we want each gene to be between a particular value, we can set these LB and UB values to constrain it to be between a lower bound and an upper bound. Non-LCON are nonlinear constraints, so we can feed it a function if we have constraints that don't fit into this AB, AEQ, BEQ format. And then finally, options are the various options we've already discussed. If you want some more information on all these input and output parameters and what they tell us, we type in help GA. Then we can have, there's plenty of information here discussing on the output side. So this tells us what the output variable gives. This describes exit flag. And then if we come to the top, it gives us an overview of what all of the inputs are. The other thing to emphasize here is that in MATLAB, it is automatically minimizing the function, not maximizing. So this is something we will discuss in class, and we also have plenty of time for you to explore these various options and input and output parameters in class using an example.